Let's see if things remain as good even after I start the recording and also sharing the screen. I think I can see only three, actually 2.5 of you. I can see a few more. Okay, that's better. Let me know if you can see my screen. Okay. Okay, you can see the screen as well as the video, right? Both. Can you see the video as well?
What video? Yeah.
It's a slide. Slide.
The slide and the video?
Yes.
Okay.
Yeah, not sure about the
Like
video.
we see your face and we see a slide titled Aerospace Structures.
Okay, good, good. Okay, so let's get going. Having something on top of my screen. Just see if I can get rid of that. Some reason it's on top of the screen. Okay, anyway, just not able to see the top of my screen. So let me see if I can instead like this. This might be better. Okay, is this better now?
Yeah.
Okay. So we're continuing with topic 3, where we were discussing what are all the things to be covered in this course and how we plan to cover it, because most of the things are fairly advanced topics, each of them requiring a course, whereas a basic introductory course like this at the undergrad level requires just the cursory overview of all of these topics. And we also saw that we can't leave them out because they're all very important concepts, and knowing them is absolutely essential in order to take this forward. So having done that in terms of what topics and how we are going to actually cover each one of them, we actually divided them into, apart from fundamentals, 5 different concepts or phrases or words, which essentially are abbreviations which start with the letter F. So we have seen how we can take the very core or important aspects of it and cover most of it in a qualitative way. Now that we are done with that aspect, we start with another aspect today, where we are looking at the various ways of classifying the structures that we would like to analyze. So this course is structural analysis, and being an AE course, it's flight vehicle structures. And within flight vehicles, there are many ways in which we can classify, whether we are designing or analyzing an aircraft or a helicopter or whatever it is, let's say a missile or a launch vehicle, a satellite, for various applications. I hope you can see my mouse as well. Moving? No?
Yeah.
Yeah.
Okay. The highlight tool, is this visible?
Yes.
Okay. So what we're going to start off with is the basis of classification. There are many different ways in which we can classify. So the first one that I was just talking about is based on the application. What kind of place eventually, or a vehicle eventually, that structure that we are designing or analyzing will get into. Next, we'll look at from the engineering stage point of view, in which stage of the engineering we are doing this structural dealing with the structure. And then we will look at in terms of the time dependency of the overall model that we are going to be using for the structural analysis. Does it depend on time or not? If it does depend on time, how does it depend on time? Next, we will look at the technique of engineering that we will employ in order to get solutions for that particular thing. First of all, formulating the problem, and then looking at solving it. Next, we will also look at the various material types, and then we will look at the classification based on what are the external loads. And this is very important and critical, so I will have a separate slide to expand on that after this. The next basis on which we classify whatever we are going to do is the flight phase, which phase of the flight the flying vehicle is in, because that makes a huge difference in terms of the loads and also the overall behavior of the structure. Finally, the most important and usually understated aspect, which is the geometry, and we will see what important role it plays, and therefore, based on the geometry, what kind of classifications we can do. Some aspects of this classification I did, in fact, in the very first class itself, so we will just go through that, right? So coming back to the first basis of classification, which is application. These are all the categories or topics that I will have on the right-hand side. So if it's based on the application, then and let's say we have an aircraft, then the aircraft could be either military or it could be civil. And within military, again, you could have fighters or bombers, etc. And within civilian kind of aircrafts, we could have transport aircraft, we could have business aircraft, we could have acrobatic aircraft for adventure purposes, sport, etc. So depending upon each one of these, the design of the aircraft changes, and therefore the design of each of its systems changes, be it the propulsive system, the aerodynamics, or the controls, etc. But our focus is on the structures. So we will see from the point of view of aircraft structures, how is it different for military and civil. We will take up some examples, we'll see cutouts, and we will see what are the salient differences between the structures there. And therefore, because there are those differences, how do we go about looking at the analysis, how is it different in the different cases. It's the same overall methodology in terms of the math and the physics, but the nuances of the end application of the techniques will change, right? So this is as far as aircraft are concerned. Next, if you look at helicopters, again, it's a very broad range of vehicles. In fact, being in Georgia Tech, that's something that we are proud of, being a center of excellence for rotorcraft technology for right from its inception. So the Army, NASA, and the helicopter industry all put together as a consortium funds a lot of research projects in Georgia Tech, apart from a couple of other universities which have kept changing, but Georgia Tech has remained the center for excellence in rotorcraft technology right from the beginning till now. And Professor Prasad is one of the leaders over there currently. So when we look at helicopters, we are looking at, again, in terms of the structures, there's a huge difference, especially the main lifting structure in the case of the aircraft is the wing, which is a fixed wing, whereas here you have a rotary wing. And the rotary wing is a much more complicated, complex animal to deal with from all points of view, including structures. because from the structural point of view, what we are looking at is a much larger axial load compared to an aircraft, because an aircraft's wing can, for all practical purposes, be modeled as let's say, cantilever beam to start with, and then of course we can introduce further complications to it. But the simplest way is to model it as a cantilever kind of a beam. But on the other hand, the helicopter, even though you can model it as a cantilever beam once again, because one end is kind of fixed, especially when you're looking at the current kind of helicopter rotor blades, which are not having hinges or bearings, which is what I referred to yesterday as the hingeless and the bearingless helicopter rotors. So in such a situation, it is, yes, a cantilever, but in addition to the lift and the drag and the pitching moment distributions on aircraft wings, here you will have an axial load coming because of the large centrifugal forces, and also all of these will be changing in a periodic manner, especially in forward flight or any flight other than hover and vertical climb. So because of that, the design as well as the analysis, there's a lot of complication that is involved. In many cases, the same geometry issues are there. Both have airfoil cross sections overall, but the internal skeletal structure is quite different. And also in terms of the taper that goes on, you'd see most aircraft will have much larger chord and thickness closer to the root, where the wing is attached to the fuselage. A similar kind of a situation arises in this case also, but because we want to elastomerically simulate the hinges and the bearings, there are certain fly drops at certain locations, and that can make the analysis much more complex. Again, in terms of that's just the main rotor, but the main rotor is not all that the helicopter is. Apart from the fuselage, it also has another complication, that because it's a rotating lifting surface, we need to balance the torque. Otherwise, the rotor will be rotating in one direction, and the helicopter will start rotating in the other direction, which will be absolutely inconvenient for the pilots and, of course, the passengers. So you need to balance that torque, for which you have anti-torque systems, which is conventionally being the tail rotor, but also you can have two rotors which are kind of parallel to. Okay, okay. Two rotors which are either side by side or front and back, just like doubles on a cycle, called as a tandem kind of a configuration, and they will be rotating in opposite directions, creating opposite torques, so that they get balanced overall as far as the helicopter itself is concerned, right? Or you could have coaxial rotors, one above the other, and both rotating in opposite directions, each causing a torque in a different direction, and therefore, once again, the fuselage will not be affected by the torque. Then you could also have instead of the tail rotor, this particular configuration, what I call as NOTAR, based on McDonnell Douglas nomenclature. McDonnell Douglas, of course, was an aircraft company which was acquired a few decades ago by Boeing, and we work very closely with Boeing. In fact, the particular facility which belonged to the erstwhile McDonnell Douglas, but is now actually in along with Boeing in St. Louis, and a lot of the research of Boeing, not only for helicopters but other aspects, takes place there. So the NOTAR is actually an acronym for So the NOTAR is actually an acronym for no tail rotor. NO comes from no, T from the tail, and the TA from the tail, and R from the rotor, right? So you don't have a tail rotor, neither do you have counter-rotating axial or tandem or side by side. Instead, what you do is through the tail boom, you blow air. There's a fan just at the intersection of the tail boom and the fuselage, which blows out air, and at the tip of the tail boom there is a nozzle, and that through that nozzle the pressurized air comes out, and therefore it creates, just like in a jet engine, and therefore just that there's no combustion involved over here. that creates the force at the tip of the tail boom, and therefore creates a force which creates the torque in the opposite direction to cancel out the torque from the main rotor. I don't know why, but that was a very interesting, intriguing concept. I did mm, uh, take forward much in terms of application to the later aircraft. Depending on each one of them, there will be subtleties from the structural analysis point of view. For example, the helicopter rotor blade, typically made out of composites, is subjected to what is known as failure called delamination. So, in other words, two layers are essentially separating out from each other, and because they are separating out, the rotor blade will not be able to take as much load as it was designed for, and there could be a failure because of that. So, if you want to be able to analyze these kinds of things, then you need to have more advanced models for the structures. In particular, for example, if you're modeling this as a cantilever, you need to take care of the initiation of that delamination and then the growth of the delamination, how the stiffnesses are affected, and therefore how the overall failure occurs. Because these are so critical that sometimes they can be quite disastrous in terms of how the overall flight happens. For example, the one of the assignments that I gave you yesterday was to work on the helicopter called ALH, or the Dhruv, the Advanced Light Helicopter made by Hindustan Aeronautics Limited, which has been around for more than a couple of decades now. But one of the initial flights that they had of their prototype, especially at an air show, that had an accident, and unfortunately it was fatal. The pilot, the test pilot who was piloting that helicopter, died as in that crash. So then they came to us for research consultancy, and based on their accident investigation, they had found out that the culprit was the tail rotor flex beam. So essentially, it is the tail rotor, as I said, made out of composites, and it's ply drop. So in other words, just like my palm, if you see towards the wrist, it is very thick over here, and then it tapers down and becomes thinner over here, so that it's much easier to bend, right? So it's essentially creating a hinge like a pseudo hinge. There's no hinge, but there is a pseudo hinge because of the thinner nature. And on some of these locations, there were damages in the composite, and which eventually made the tail rotor to fail, and therefore the anti-torque was not no more active, and the helicopter had to crash. So they wanted what is known as a real-time health monitoring system, so that the pilot can know the status of not only the tail rotor but also the main rotor, all the primary load-bearing structures, so that if there is an issue with it, the pilot can make an emergency landing at the nearest spot that is available. And so when we started doing that, we came up with a solution which is now on the flying helicopters, and that and many other design changes, other things that they did, have gone a long way in terms of making this helicopter one of the safest helicopters since then. When we do the structural analysis for this, we need to take care of some of these complications, so which is what we have to be aware of. So in this particular case, there's what is known as an extension twist coupling. So in other words, you're extending because of the tail rotor blade, as well as any rotor blade, because of the centrifugal forces that gets pulled, and because it is getting pulled, and the pilot is applying the cyclic controls as well as the collective controls through the pitch sticks that he has. And these are in turn causing the twist of the blade, uh, which is periodic in nature as it goes around. And that creates um, both simultaneous extension load as well as torsion load. Of course, there is also because of the lift, there is the bending load, and because of the drag, there is the bending in the other direction, what we call as the flapping direction and the lead lag direction. But all of these put together, some of them get more coupled with each other than the other. In particular, from a structural point of view, it is the extension and the twist which get coupled, and because of that, there can be certain issues. But if it is done properly, it can be to an advantage. So whatever causes harm, actually, if you look at it from a different perspective, can cause benefit as well. In other words, many of these are like, especially the couplings that come from geometry and or material, are usually double-edged swords. So you can either use them or misuse them, or suffer because of that. Okay, so which means that we should be aware of, in a structural analysis, how these things get coupled. So I can't study extension alone separately and torsion alone separately. I have to study both of them together, because one causes the other, and without knowing how they are related to each other, I would be just working on a theoretical problem of no practical relevance. So going forward, we'll see the next category is of applications is missiles. Once again, within missiles, you could have various things like SAM, which is the surface-to-air missile, AAM, air-to-air missile, then air-to-surface missile or surface-to-surface missile, etc. Uh, Also intercontinental, ballistic, and so on and so forth. Though a lot of these differences are also in terms of the other aspects, like the propulsion, the propellant involved, etc., the overall design. From a structural point of view, also the loading cycle from the time the missile is fired to when it hits the target is quite different. The loading cycle being different, the structural analysis also becomes different, and that's very, very important. And very interestingly, there's a lot of similarity between missiles on the one hand and launch vehicles on the other hand, because both of them predominantly use rocket vehicles as like rocket engines. And therefore, you will see that a lot of these technologies are interchangeable, which is why they're called as the dual-use technologies. And you'll see a lot of sanctions, and the technology transfer between nations will be usually difficult even for launch vehicles, even if they are just having civilian applications, because the same technology can be used or misused by certain rogue nations for missiles. So coming to launch vehicles, this is another part of your assignment which I gave yesterday, where we talked about two LVs, LV being short for launch vehicles, the polar satellite and the geostationary satellite launch vehicles. Which is what I've written at the bottom as well. So depending upon the launch vehicle, how many stages it is made out of, because most of the launch vehicles these days, depending upon the task that they have to undertake, the payload that they have to deliver, and to which location they have to deliver, in which orbit that is, will be quite different. And the number of stages are usually quite a few, and there are also boosters, etc. And each of them will have their own complications in terms of the structural analysis, more so here compared to aircrafts, because even though aircraft have a fuel burnout, and by the time you are landing, the weight of the aircraft has reduced compared to when it has taken off, and therefore the structural analysis has to account for these different weights, not only in terms of an overall sense of how much the weight has reduced by the amount of fuel consumed, but also in terms of the weight distribution, because where that fuel was stored, maybe it's in the wings, or maybe it's in the underbelly of the fuselage, depending upon the type of aircraft and how the fuel is burnt out. All these things will come into picture. And when we study bending, we will see some very interesting concepts of the advantages and disadvantages of where you store the fuel, and also how you utilize the fuel, which part of the storage tanks you utilize first and which you utilize later, are all based on structural considerations, interestingly. And we will see why when we get there. And there are also some simpler rockets like sounding rockets, etc. But some of the basic concepts in terms of how these are handled remains the same. This is a little bit of noise coming from your end. So if all of you can mute your microphones unless and until you're asking a question, that will be great for the recording as well. Perfect. That sounds very nice now. Okay. Next category of vehicles that we will be dealing with are the satellites. And when we go to satellites, once again, just like in the launch vehicle, there was a PSLV and GSLV. The reason why they are named that way is because of the kind of satellites that they're dealing with. And therefore, that is geostationary or polar, etc. Right. So geostationary is typically looks stationary with respect to the Earth, because the Earth is also, remember, rotating and revolving around the sun as well, rotating on its own axis and revolving around the sun. And this the satellite goes along with it in such a way. Of course, it's moving, but when seen from an Earth-fixed reference frame, it feels as if the satellite is not moving, and that's why it's geostationary. And based on some very simple high school level physics calculations, we can show that it just has to be at about 36,000 kilometers altitude in order for that to happen. That's, of course, not part of the syllabus of this course. It's something that you'd study in dynamics, for example, or more advanced courses on dynamics in terms of more involved things. But though it's a fairly simple derivation in terms of high school math and physics, right? Next, we talk of again in terms of the speeds at which any of these might be flying, especially in case of aircraft. You could have low subsonic flights, whereas most others are flying at very fast speeds, high speeds, and Mach numbers which are closer to 1 transonic and greater than 1 supersonic and much greater than 1, around 5 or more hypersonic kind of aircraft. And each of them have their own nuances. For example, the hypersonic kind of aircraft or any other flying vehicle will have the issues associated with the drag because of the shock waves, and in particular the wave drag that comes out of it. Therefore, the additional load that is there on the structure because of that, both in terms of shear forces and, more importantly, bending in the lead lag direction. So those things are going to be in the case of the aircraft, fixed wing aircraft, we don't call it lead lag, but we call it I'm sorry, there's this procession going on close to my place, so you might hear some music in the background. I hope it's not too much of a disturbance for you. It should be within a minute or two, it should pass by my home. So continuing, we are looking at the polar, geostationary and polar satellite. So we already covered, and the speeds we have covered. Again, in terms of the specific application, like whether it is an airframe structure or an engine structure, for example, or a re-entry modules structure, the kind of loading scenarios and how the load changes over the phases of flight are going to be very different. For example, in the airframe structure, very little bit of thermal analysis needs to be done. Whereas unless it's very close to the place where the engine is mounted or something like that. But remember that the aircraft also fly at a fairly high altitude, and the temperatures are quite low over there compared to the sea level. Sea level temperatures, again, different at different locations around the world and in different seasons around the year. So though there are some thermal related issues with airframe structures, they are not as severe as those with the engine structures. So when you're designing structures for the aircraft engine or any other flying vehicle's engine, the thermal analysis or the thermostructural analysis becomes much more critical, the coupling between them. Finally, in terms of a re-entry module, when essentially the vehicle is supposed to be reused and therefore comes back to Earth, and when you're having that kind of vehicle, it faces a very large thermal load on its re-entry, because it is going through the atmosphere at a very high speed, And when it is doing that, the thermal loads that get generated are so severe that the re-entry module structural analysis is very different. Of course, you'll have a lot of active cooling and also tile structures, ceramic tiles, etc., and how they're going to be transferring the load between them and what kinds of failure could occur over there are very, very different from what we consider with typical airframe structures like just a wing or a tail. So that's as far as the applications are concerned. Are there any questions on the first category that we just looked at for the classification basis?
I think we're good. No questions for that?
Okay, thank you. Let's go ahead. So next we look at the classification based on the stage of engineering that we will be dealing with in an analysis. So for most part of this course, we'll be only dealing with analysis. That's in fact in the very name of this course. That is required for an existing structure or something that you can imagine. That is, let's say it's you have conceptualized already. So you have a conceptual design. So you're just analyzing that structure which is only on paper, not an actual flying vehicle, right? So you could do that, or you could be doing an analysis after an aircraft has been already designed, prototyped, and commercialized because it has some issues, or you want to improve the design, or you want to go to a new version of the same aircraft. Let's say, for example, many of these aircraft, let's say by Airbus or Boeing, will have the same three digits, let's say it's 787 or 350, etc. But then they will have a dash and then something else as an extension to it, which is essentially a modification of the same platform with newer technologies for better utility based on the feedback that they get from their customers, which is the airlines. Right. The next important thing, as we already discussed in the first class, is the design. In analysis, we'll be breaking up the overall aircraft, first of all, into the wing, tail, etc. And within the wing, we'll be breaking it up into the skin, the spars, the transverse ribs, etc. And analyzing each one of them, also taking into account how the interaction with the other components happens, and therefore how the loading conditions, boundary conditions have to be taken care of. But the important thing is in analysis, as opposed to design, we are looking at the breaking up of things, whereas in design, we are looking at a synthesis or putting together of things in a holistic manner. So that's the second stage of engineering. There's also the analysis of the stability of the vehicle as a whole, stability and control, which involves the stability in the various dimensions in which it is there, and also the various rotations that are involved, like the pitch, roll, and yaw. So the roll and the yaw are coupled with each other and with the sideway motion, whereas the pitch and the vertical and the horizontal motions are coupled with each other. So there is a stability associated with that, and how the loads vary will have an implication as far as the structural analysis is concerned as well. And within structural analysis itself, you have stability or instability, as we saw yesterday, in terms of elastic instability like buckling, either globally or locally, including wrinkling, crippling, etc., or in terms of an aeroelastic sense like flutter, or which is a dynamic, or divergence, which is a static phenomena. So those studies are another stage of engineering that we typically deal with. The another thing which has become very critical especially in the last couple of decades, is the health. The health of the aircraft as a whole, of its various systems, subsystems, and in particular our health that we are talking about here is the structural health. And typically you need to monitor that. What is abbreviated as SHM, structural health monitoring, has become a very large body of not only research but also courses for teaching and for learning, even at the very basic levels. Now, this health is not only monitored, in other words, the diagnosis is done, but also prognosis is done, because we want to see based on the current health and how that health has changed over a period of time, can we make predictions about how the health is going to be as we go forward in the future. So that aspect of health, if we want to understand, we will have to look at the mechanics of the damage. What is known as damage mechanics involves fracture, various aspects of the composite failure, like delamination or the fibers breaking or the matrix cracking or the fiber matrix interface, which is getting debonded, etc. So these kinds of things you have to ensure are part of the analysis. Otherwise, it will not be useful in scenarios where these things occur. It may not have caused a major accident for the aircraft as a whole, but in terms of the MRO operations, that is the maintenance, repair, and overhaul, a lot of these analyses are required in order to take the appropriate action, what needs to be repaired, what cannot be repaired, and therefore needs to be replaced, etc. Right? And then we talk of the life estimation, extension as well. So this is once again both at the structural level as well as the whole vehicle level. So the whole aircraft is designed for a certain period of time. So based on these analysis and health monitoring and prognosis as well, we can many a times estimate how much longer it can last and through what kind of operations. And therefore, we first need to estimate the life, and then we can extend the life. So these are again very important parts of structural analysis as it is done today. So next, so that's as far as the engineering stage is concerned, in terms of the various kinds of things that are required from a structural point of view. Next, we go to the classification based on the dependency over time. As I said, the spatial variable is one of the independent variables. So this concept of independent and dependent variables is something that you would have come across in the course on differential equations, one of the prerequisites possibly for this course. And therefore, you would have seen there that there are two classes of variables, one which is dependent, which we don't know how it behaves, and the independent variable, which is the field on which the dependent variables are defined. So in most cases for practical problems, the spatial field is three-dimensional, the way we as human beings visualize the overall whatever we perceive through our sense organs, be it our eyes, ears, the nose, the tongue, or the skin. Through these sense organs, essentially we are able to perceive only three dimensions, and therefore those are the three dimensions. And typically you have an orthogonal system to deal with that, though it's not necessary. You can have non-orthogonal systems. Usually we use a rectilinear system, in which case all the axes are straight lines. But again, that is not necessary. You could have curved lines, what are known as a curvilinear coordinate system. But essentially, three different directions, which are not, none of which are the same, what we call as collinear or collinear. And therefore, in other words, they cannot be parallel to each other, right? So now, when you have these three dimensions, you have a spatial dependency. Those are the independent variables. For example, I can call them as x1, x2, and x3. On the other hand, if you're looking at time dependency coming in, that becomes a fourth dimension. It's very difficult for us to visualize, but because we have a sense of time, because we are physical ourselves. So when do we say something is physical? Is something which can be governed by physics. And what can be governed by physics is that which has boundary conditions and is therefore subject to a boundary value problem. So in differential equations, you would have stated that just the equation is not enough, because that will give you only general solutions. To get to the particular solution and to be able to solve it fully, you need to, in terms of all the constants that you have brought about as part of the general solution, you will then need certain conditions, and those are usually either initial value problems or boundary value problems that result because of that, because of initial conditions and our boundary conditions. So our body is essentially having a boundary. It starts at some place, ends at some place in terms of a spatial sense, though our sizes might change over the age. It does change, at least in the childhood, and for many people over even in adulthood. But that is in terms of the spatial boundaries of our body, which is very clear. So we know where we are and where our body is and where we are not. Similarly, in terms of the temporal level, we have a certain initial condition, which is our birth, and the final condition, which is our death, right? So and of course, the way the disintegration of the body takes place depending upon how it is decomposed, right? So, similarly, because of the physics involved with our body, the physics involved with our sense organs, all of these things that we do in terms of engineering, for example, flying or flight vehicles or aerospace, is essentially doing what we can do in a better, faster, or a more economical way. So that's essentially what we are trying to do. For example, if it's, let's say, a vehicle, essentially you're trying to go faster than you could walk. And if you're flying, essentially you're looking at birds and saying they can fly at a certain speed, I can fly faster. Migratory birds, of course, can fly large distances, which is also an inspiration for long haul flights and things like that. So we get essentially the inspiration from that. And so what governs our biology or the physicality is what governs eventually your time as well, the engineering as well. And so from that point of view, these four dimensions become important, and that's where the time dependency comes in. And when you don't consider that time dependency, you're dealing with a subject called statics. And the entire course here will be dealing with only statics. We'll only be looking at these three dimensions, x1, x2, x3, and leave out that fourth dimension of time. Uh, which we can't visualize in terms of a graphical depiction over here. But even those three dimensions, in fact, we will cut out one of the dimensions, as I was showcasing in examples in the very first class in the aerospace engineering department, where we said that if one of the dimensions is small, like if it's a plate, then we will essentially be leaving out the thickness, and therefore when we leave out the thickness, it's only the breadth and the length that come into picture. Once again, if we deal with this as a beam, we will leave out not only the thickness but also the breadth, because both the thickness and the breadth are small compared to the length, and therefore you're dealing with only one dimension. So uh, from a perception point of view, human perception point of view, we can see only four dimensions, though there are other dimensions that science has explored already. But from purely from our perspective, we can see or experience rather than see, experience only four dimensions. But then for the simplicity of the engineering and for the right reasons, because we can get still accurate results, we keep dropping off. For statics, we drop off time. For essentially the plate or shell analysis, we drop off the thickness. Again, becomes two dimensions. Then for the beam, we drop off even the breadth, and therefore not the breadth, but the breadth or the width, and therefore it becomes a one-dimensional problem. So essentially, you're reducing the number of independent variables. And now again, if you go back to your differential equations course, you will see that what is the implication of this. There are two types of differential equations: ordinary differential equations and partial differential equations. Ordinary differential equations depend on only one variable, much easier to solve in an overall sense, though there can be a few complicated ODEs as well. Mm. On the other hand, the PDEs, the short form for partial differential equations, have more than one independent variables. Like, for example, in our example, instead of only x1, you have both x1 and x2 for a plate or a shell, all three x1, x2, and x3 for a three-dimensional body. Or in a dynamics problem, you have x1, x2, x3, and time. So when you have more than one, irrespective of how many, whether it is two, three, or four, you're essentially ending up with kind of a more complex mathematical construct for your boundary value problem and or initial value problem. Uh, but the very interesting thing is that whatever statics that we will study over here is actually going to be relevant even for dynamics, when if at all some of you are taking more advanced courses in structures and look at structural dynamics, etc., then you will see that a lot of things that we come up with here, even though they are for statics, they become valid for dynamics problem also, because, for example, if it's a beam kind of a problem where the breadth and the thickness are very small compared to the length, the analysis that you do at the cross-sectional level, that is wherever you cut, you have a breadth and the thickness. That is what we will be predominantly doing in this course. We will be trying to see if I want to shrink this area to a point, that is this cross-sectional area to a single point, then I have to lump all of the properties that are distributed over here in an appropriate manner at that point. When I want to do that, what I'm actually doing is that I'm reducing that uh, two of the dimensions from the overall dimensionality of the problem. So when I'm doing that, for these smaller dimensions, whatever we do, that is usually not dependent on time, even in a dynamics problem, where the overall vehicle or the overall structure might be time dependent, the having facing time dependent loads, and therefore its response is also time dependent. But the cross sectional behavior will not be time dependent, or it will be negligibly dependent on time. And therefore, since most of our focus is on the smaller dimensions, be it a cross section of a beam or the thickness of a plate or a shell, therefore these things remain valid when we go to a dynamics problem. So this is something that you should be aware of, that whatever I study here in a dynamics scenario can still be useful, because without this understanding, most people think that they have to start afresh when you're looking at dynamics. No, many of the takeaways that you have from this course will still be the starting points for can be the starting points for your dynamics problem, both in terms of the formulation and the solution. And that's a huge advantage that you have. And otherwise, you would not be even considering studying a separate course on statics and then this course on structural analysis, where in both of which you're not invoking the fourth dimension of time at all, the independent variable of time at all, because these have implications, like the statics course that you took had implications for the dynamics course you took later on, which is why that was a prerequisite. Similarly, whatever you're studying over here will have implications to more advanced dynamics courses that you may take in structural analysis and or design as well. Next, in terms of dynamics, again, it's the various kinds of dynamics or time dependencies that are involved. One aspect of it is the vibration, which is essentially a motion which is happening in a time-dependent way, and that time dependency can be caused by just the overall structure itself, because of some disturbance that it has encountered, that it's vibrating, what we call as free vibration, or it could be forced because of in the presence of an external force or a moment, or force distribution or moment distribution, all of which in general we will just call as a single word load, because of a dynamic load that exists externally, and that's forced vibrations. And there could be random vibrations because of, let's say, gust and things like that. And sometimes some of these studies from a theoretical point of view, even when those loads are not occurring, can actually help you as building blocks for a much more complicated scenario that is encountered in reality. That is one kind of dynamic study. The second kind of dynamic study is what is known as impact. So essentially, this is something again which is time dependent, but most people don't realize the time dependency because it happens so fast. Okay, so it's essentially like a pulse in terms of the loading. So, and that pulse time duration in the limit that the time duration tends to zero. So in other words, like a hammer, when you're hitting something with a hammer, obviously it's going to cause an impact on that. And so how the structure responds to that is very different, even if the overall force that is applied is equal to a static load of the same weight of the hammer. Let's say if I just keep the hammer on the structure, how it behaves, and rather I hit it with a certain impact velocity, what happens? Again, whether it's a low velocity impact, typically less than 10 meter per second, or a high velocity impact, or somewhere in between a medium velocity impact, all of these will have different behaviors, because the material behavior changes, the geometry can get modified because of damage and other things, and there's a certain energy absorption which takes place, and that's a study by itself. Again, impact mechanics is a course by itself. Finally, fatigue, which we already talked about in terms of cyclic or periodic loads. So I'd not like to repeat that. So are there any questions on these two classifications that we just studied, engineering stage and the time dependency?
No questions.
Okay, thank you. So next, let's move on to the fourth way of classifying what we are going to study. That is based on the engineering technique. What kind of technique are we going to use in order to make the analysis, right? So that technique for a long period of time was purely experimental uh, because a lot of things are not sure unless and until you have done an experiment. Only then you can be absolutely sure that whatever you have done with pen and paper or with the computer or a calculator, or even AI or ML is something that works, right? So that's what we call as verifications and validation. So these two are terms that are sometimes interchangeably used, but it's important to understand that you are um, uh, it's again from a software terminology, you will see that depending on whether you're comparing with a theory or with an experiment, the terminology is going to be quite different. So coming to the experiments, again, because we're talking of flight vehicle structure, structural analysis of that, some of these experiments could be done on ground, on the overall aircraft or on parts of the aircraft, the components of the aircraft, like the entire wing or parts of the wing, etc., depending upon what is the intent of the experimental study. And some of these could be flight tests as well. On the flight, you put some sensors onto some of these components and you monitor those. You essentially acquire the data and eventually you tend to analyze the database. And that's what we tend to do as far as the flight-based tests are concerned. Again, these tests could be either DE or NDE, which means destructive evaluations or non-destructive evaluations. Sometimes you use DT or NDT, where T stands for testing, that is destructive testing or non-destructive testing. So destructive testing, you take it all the way to failure. And that's something that you must be familiar from the automobiles as well. You like your cars and or two-wheelers are also subjected to tests which are called as crash tests for crash worthiness, etc. So you actually destroy the prototypes in order to evaluate how the damage occurs and how the energy absorption happens. And that's the impact mechanics that we just talked about in the time dependency. So that's also something that has to be done for a few cases because those are mandatory requirements, even for aircraft from a FAA point of view, based on the corresponding FARs, and similarly for other countries as well. Other than the US. That's as far as the oops. Yeah, so that's as far as the experiments are concerned. Uh, Destructive and the non-destructive evaluations, of course, many different ways of doing it, like X-rays, ultrasonics, etc., thermography, radiography, various other kinds of things that are used, which do not destroy the structure, but still get a lot of useful information. And this has become a very critical part of a lot of aerospace structural analysis and design as well. Apart from experiments, the second way of dealing with things, and this was the way in which this particular course was taught when I studied it, and to a large extent, many of the universities continue to teach it in that way. It's a purely theoretical study where you end up with certain analytical results over that, and at the most, people might take you to numerical results. But as I said, most of the analysis these days is numerical because of the extreme complexity of the structure that is used for most of these aircraft applications or any flying vehicle applications for that matter. When I say complicated, because of the material behavior as well as the geometries. So the intricate geometries involved at the skeletal level, we saw some cutouts already. We will see a few more cutouts probably in the next class. And when we see these cutouts, we'll see how for a layman looks so ugly, but that's essentially how the load transfer takes place between one part to the other part, and we do it in such a minimalistic way, of course, inspired by nature, but has developed in engineering sense, also to a large extent by human beings over the last century that the flying vehicles have existed. Of course, there's a lot of knowledge which has been borrowed from other structural engineering aspects like civil engineering structures, etc. But of course, we can't apply it blindly, and that's why we looked at in yesterday's class the differences in terms of some of these structures, how they are for civilian and the flying applications, right? So coming to the numerical approaches, or for that matter, analytical approaches, once again, another way of classifying instead of analytical, where you're just doing it in a symbolic processing. And these symbolic processing also nowadays doesn't need to be done entirely by hand. A lot of it can be done by using symbolic processing tools like Mathematica or Maple, or to a rudimentary extent, even MATLAB can do it, though MATLAB is more powerful for numerical techniques than for symbolic processing. From a symbolic point of view, Mathematica, Wolfram, and Maple have been existing for a long period of time. And there are many, many others who have come up since then and specialized for different kinds of applications. But the last thing that I want to mention is what I call there as variational and equilibrium based. So variational principles are Lagrangian or Hamiltonian, named after Lagrange or Hamilton, or many others were pioneers who have worked in that field, and not only after them, but a few before them. Unfortunately, their names are not taken as often as those of Lagrange and Hamilton. And before that, of course, the equilibrium-based approaches, which is essentially the force equilibrium and moment equilibrium, which is Newtonian mechanics, named after Newton. And again, a large bunch of scientists who have been involved both before and after Newton. In fact, if time permits, at the end of the course, if I'm done with all of the syllabus for the structural analysis, I will talk to you a little bit about the ancient Indian contributions towards these as well, which unfortunately are very less known. But that's only if and only if I'm done with all of the things that need to be done from the syllabus point of view over here. So coming to the variational approaches, these are essentially energy-based approaches, and they involve certain optimization in terms of a total potential energy or some kind of a functional that is defined. Functional is something that is beyond the scope of this course, but essentially for your purposes, you can think of it as a function of functions, which needs to be determined. And that functional, when you're trying to minimize, which could be the total potential, for example, or the Lagrangian or the Hamiltonian, you end up with a solution for that. And for simple problems, both the variational as well as the equilibrium-based approaches, if formulated appropriately, will lead you to the same result with the different levels of difficulty or challenges in terms of leading you to the solution. But the beauty of the variational principles is most of these are defined over quantities which are not vectors or tensors. Though they might be defined in terms of vectors and tensors, eventually the final quantity that you want to optimize or usually minimize is something which is a scalar quantity and therefore doesn't have directions as only a magnitude, and so much easier thing to deal with. And a lot of takeaways are there in terms of understanding the overall physics of the problem from various aspects of the intermediary results of variational approaches, which advantage you do not get usually with the equilibrium-based approaches. So whereas for simple problems, it's okay to go with equilibrium-based approaches as and when the complexity gets higher, which is the case for structural analysis in aerospace. Variational approaches are the best. And the variational approaches, another importance of that is the fact that the current way in which almost the entire industry works, the finite element method, is based on those variational principles. And so if you understand the variational principles, you understood the very basic building block, the physics of and the math of the finite element method or finite element analysis as well. And that's quite useful. Coming to the next level of classification, that is in terms of the type of material that is used. Uh, and again, you'll have multiple materials which are used in the structure, and that includes, for example, the homogeneous and the non-homogeneous classification, where, as I said earlier, uh, within the material, different points will have the same properties, therefore they're homogeneous, or if they have different properties, then they're called as heterogeneous or non-homogeneous, right? And composites are an example of that non-homogeneous category. The second classification also is something that we have seen. The word comes, isotropic comes from two parts, iso and tropic. Tropic means direction, iso means same. So same in all directions. Earlier we were talking in the case of homogeneous, non-homogeneous, two different points we were considering. Now, in the case of isotropy and anisotropy, we are considering just a single point, and at that point, we want to check what are the properties in different directions, right? So, if the properties remain the same irrespective of the direction, we call it isotropic, and we prefix it with an to make it negative and call it anisotropic if it is not. And there, of course, there are special cases of anisotropy like orthotropy, etc., some of which we will consider because they are relevant to the structural analysis of aerospace vehicles made out of composites. The next thing in terms of the material, the way we analyze is a structure is through linear material models or non-linear material models. So for most part of the loads are very, very small, you will end up with smaller strains. And if the strains are small, you will end up with a linear model being good enough. But if the load reaches such a level or the structures are so thinly made that it's not able to handle the load, then the strains can become very large. And when the strains become large, the stress strain behavior becomes nonlinear. So in other words, if I plot the stress versus the strain, if it's a straight line, it's linear, and that is valid for very small values of strain. But as you go for larger and larger strains, that curve, the stress strain curve can become nonlinear, especially for ductile materials like metals. And therefore, you need to have an understanding of material nonlinearity. Luckily, for most polymer matrix composites, they have a brittle behavior like ceramics. You know, like for example, if your cutlery breaks, how it breaks is very different from how a metal structure breaks, right? It goes through a process which is actually kind of almost physically visualizable. Whereas this happens much, much faster, the fracture of ceramic. So to some extent, the polymer matrix composite, especially with thermosets, thermoset matrices like epoxy, behaves in that manner, and therefore you do not deal with too much of a material nonlinearity in most polymer matrix composites, but you do need to deal with them in the case of metals because beyond the yield or the nonlinear limit, usually the linear limit or what is called as the proportionality limit, beyond that you will have a nonlinear behavior for most metals. Then there is another classification based on whether it is elastic or not elastic, what we call as inelastic. And within inelastic, one special category or an idealized version of inelasticity is plasticity. We will, of course, revisit this in terms with equations and things like that, because we are going to cover the theory of elasticity as a review, because that's very important to understand the physics of the structural analysis going forward, and therefore the elasticity will be covered. But to put it in a very, very simple way, what does elastic mean is that the stress and the strain are having a one-to-one relationship. So in other words, if I give you the entire for this whole structure, let's say this is an aircraft wing, I give you the strain at all points at a given point in time, I will be able to determine the stress also at all points in all directions at that particular point in time. So that is essentially elasticity, where there's a 1:1 correspondence between the stress and the strain. So there are no other variables which are impinging. So it's the other way around is also true, that if I give you the stress field distribution throughout the wing, then you should be able to get the strains also at each and every point in all the directions, both the normal stresses, strains, as well as the shear strains. So that's as far as elasticity is concerned. Whereas another way of looking at it is if I load it and then I unload it, it comes back to its original shape and size. So that means that the whole structure is made out of an elastic material, and or the load that we have subjected it to has not taken it beyond that elastic limit, and therefore it has come back to its original size and shape. So it's very important, both the size and the shape, because those are the two aspects of geometry as we already discussed, right? Whereas in inelasticity, you have some kind of a change in shape or size even after the removal of the entire load, and plasticity is a very, very special case of that. So we will not, of course, venture into any one of those things, but it's important to be aware of these terminology, because very, very critical in understanding whether whatever you're doing is really applicable or not. At the end of the day, it should not become something that is just giving you intellectual satisfaction of no practical relevance. Another way of classifying the materials is in terms of conventional materials and what are known as multifunctional materials. And within multifunctional materials, the category of smart materials that I very briefly touched upon when I was introducing our lab in the first on the first day, the CAD lab. The M stands for multifunctional over there. And within that multifunction, I also mentioned that there's a special category called smart, where there is co-located sensing and actuation, which is done by the structure itself, by the structural material, which is load bearing. So in addition to the load bearing functionality, it has two additional functionalities of the sensing and the actuation, and therefore it's able to adapt itself, or what is known as an adaptive structure. And the specific material that you use in order to achieve that, it could be a shape memory alloy, it could be a piezoelectric material, it could be a magnetostrictive material, it could be magnetorheological or electrorheological. Within piezoelectrics, again, you could have piezoceramics, piezopolymers, you could have wafers, films, and also piezo composites. Excuse me. So these kinds of possibilities make the analysis slightly more complicated, because you have to take into account not only the stress and the strain, but also how these are getting modified because of the presence of these other physics that is involved. For example, in the piezo, it's electricity, which electric fields, which comes into play. In the magnetostrictive, it is the magnetic field and the magnetic theory which comes into play. So essentially the electromagnetic theory. In a shape memory alloy, the changes in the internal structure of the material based on the temperatures that, for example, in an example of a shape memory alloy is nitinol, made out of nickel, titanium. So that is something which will have two different phases called austenite or martensite. And then you will have different internal crystalline structures, and based on that, the properties will vary. So those can be taken advantage of. So some of them are much better as actuators. For example, piezoceramics. Some of them are better as sensors, like the piezopolymers. So depending upon that, once again, the kind of application and also the kind of analysis that needs to be done, there are subtle differences. Any questions on the material type?
No.
Okay. So then we will go on to the external load type. I will spend less time on this because I'm going to cover that with a separate slide afterwards. So some of the kind of loads that you could have from an exterior to the aircraft itself is in terms of the Earth or whichever atmosphere that it is flying in. The gravitational field is going to cause a certain weight. which is acting through the CG in a very simplistic way, but in reality, it's actually a weight distribution depending upon how the material is distributed along the length of the aircraft, along the span of the aircraft, along the height of the aircraft, how it gets distributed in different parts. That will make a difference. This is especially important uh, in terms of the distribution when you go to much longer or larger structures, like, for example, space booms. So in satellites, even though while launching and at the point of detachment from the launch vehicle, the payload, which is a satellite, might look very small. After it gets into its orbit, typically certain antennas are deployed, and some of these antennas are fairly longish structures, and therefore, and since they are quite far from the Earth as well, you will see that there can be a gradient that is involved as far as the small g, that is the gravitational constant, is concerned as well. And also, some of these might have influences of not just one planetary body like the Earth, but also maybe, let's say, the gravitational effect of the moon. For example, if it's still in an Earth, uh, in an orbit around the Earth, depending upon the moon going around the Earth, you could have certain gravitational fields of that influencing it in a certain periodic manner, fairly complex behaviors. So all of these need to be kept in mind, especially because there's a lot of work going on interplanetary motion in terms of our interest in looking at studying Mars and Venus, and also some of the satellites of other planets like Jupiter and Saturn's satellites, like, for example, Titan, a satellite of Saturn. That is something that is of great interest to us because of the conditions being somewhat similar to that of the Earth, compared to many other planetary bodies. So, depending on that, you need to understand the implications of the gravitational field, and this can sometimes play a very important role, because not only does it cause body forces, sometimes it can cause body moments as well, and we will come to understanding what these mean in a later class when we are actually introducing simple equations in order to understand these loads. The second category of loads are the inertial loads. Uh, Once again, it's very important in a dynamics problem, and also aerodynamic problems, and dealing with dynamic aeroelasticity, etc. But even from a purely structural point of view, when you're dealing with structural dynamics, you will be dealing with inertial loads. Inertia, as you know, is just a property that makes somebody just lazy. Just you want to remain in status quo. You're just in the comfort zone. So you don't want to make any changes, or you're resisting changes, right? So that's essentially what is talked about in Newton's first law, where he says that a body in a state of rest remains in a state of rest, or a body in motion remains in the same state of motion unless and until acted upon by external forces. And forces include, of course, moments and force distributions and moment distributions as well. So essentially, remaining at that status quo is not something that is happening over here, but there is also a tendency to do that, because that is a very basic characteristic or nature of materials to remain in the state that they were in. Okay, so when they are subjected to certain forces and moments to make a change, there is that resistance, and that resistance, or the force that comes out of it, usually referred to as the d'Alembert's force, needs to be accounted for in the dynamic model, and that's where your inertial loads come in. They come in the moment equations as well. Again, it's beyond the scope of this particular course, but not a very complicated thing, and it is usually dealt with in other dynamics courses, not your basic dynamics course. So then, of course, there are the most important mechanical loads that we're talking about here. Once again, the mechanical loads could be because of certain impact. Let's say there's a maintenance going on, and there's a hammer dropped by a technician who's working on the aircraft. That can cause some damage, or sometimes it may not be visible, what we call as the barely visible impact damage, BVID. and those kinds of things. And then also external things like bird hits. So a bird can come and have an hit, either hit the engine or let's say the nose of the fuselage or the leading edge of the wing, etc. Because of which you will see certain different configurations of materials which are used for the leading edge. Though the shape of the nose of the fuselage or the leading edge of the wing, etc., all dictated by the aerodynamics team. In terms of what material you can use to achieve that shape, you have, as a structural engineer, all the freedom to do so. And you will use different materials depending on certain regions of the aircraft which are more susceptible to impact, or certain regions which are less susceptible to impact. And this observation will be of very critical nature for your second assignment, where we talked about for each one of those classes of aircraft, if you're trying to find which materials are used and which part of the aircraft they go into, you will see this difference. For the nose of the fuselage, the leading edge of the wings and the stabilizers, and some parts of the engine as well, you will see that there is going to be a difference in terms of the material used, and because the material used there have superior impact responses. In other words, they are able to absorb more energy. And it becomes even more critical when there is a ingestion of a bird into the engine, and it hits the tail, the rotor blades of the either the fan or the compressor or the propeller. Then you will have a severe issue unless and until the design takes care of it. And the design does take care of it, because the certifying agencies have certain very critical requirements related to that. In fact, we work closely with some of the engine companies, and we work on what are known as containment structures, which are a requirement for all aircraft engines, where within the engine housing, you will, within the nacelle, you will have what is known as a containment structure, so that if at all there's a bird hit, and let's say one of the blade breaks, and that obviously, because it is rotating, there's a huge centrifugal force, and that centrifugal force is going to make the blade to come out of the engine housing, right? So this containment is designed in such a way that even in the worst case scenario of a blade coming out, it will be contained within the engine. It will not come out of the engine, because if it comes out of the engine, there's always a possibility of it coming and hitting the wing, or it coming and hitting the fuselage, and a much larger damage to the aircraft as a whole, and could be quite uh, disastrous for the overall aircraft in terms of the way it crashes. So that these are kinds of things where, once again, material choices have to be made, geometry choices have to be made, larger energy absorption materials have to be dealt with, etc. So all of that comes into picture in these mechanical loads. And the most important thing, of course, is the ADN. What I referred to there is the aerodynamics load, uh, lift, drag, the pitching moment, the rolling moment, the sideward force, which is usually very less, unless it's a helicopter, etc., which is tilting its rotor in one direction in order to fly sideways. Then, of course, the yawing moment as well. So all those things are the loads. And again, the lift is not just a single force, but it's a lift distribution along the entire span of the wing. So along either half, the right and the left, the port and the starboard wings will have a certain lift distribution. The simplest uh, approximation to that is an elliptical kind of a lift distribution, where at the wingtip there's hardly any force, and it becomes bigger and bigger as you go towards the root, and which is why you would see that the cross-sectional size is also very different at the tip and at the root. You'll have much larger uh, chord and much larger thickness where the wing is attached to the fuselage, as opposed to the tip of the wing, where it will be fairly thin, because the loads are less, stresses are less, and therefore you don't need much material there. So This is the ingenuity of human beings, by engineers in particular, by observing, designers even more particular, observing nature and seeing how birds fly, how insects fly, and trying to see. Of course, they are using flapping wings, whereas here we are looking at fixed wings or rotary wings, etc. But still, some of the knowledge is carried over from there and adapted in an appropriate way. Right. So the next thing is, of course, the thermal loads, which you already talked about, especially important in engines, but also in aircraft flying over various ranges of altitudes. Next is, of course, from the engine, you get the thrust, and that thrust load acting through the axis of the engine. And also some of these engines have vectoring nozzles. So you will have the nozzle, which is changing its axis uh, through certain actuators, and therefore the force direction changes from the nozzle. And this is especially for fighter aircraft. You will see thrust vectoring taking place. But even for other aircraft like passenger aircraft, you will see that there's multiple engines that are there. Whereas in fighter, you can even fly with a single engine, because that's what is allowed by the FAA regulations. Because for passenger aircraft, you need extra safety, redundancy in case one of the engines fails, by appropriately deploying your rudder and the ailerons, the pilot should still be able to land. Similarly, in the case of a helicopter, there's a feature called the auto rotation, whereby even if the engine fails, the pilot will immediately disengage the engine from the rotor. So whatever momentum the rotor already has, utilizing that, he or she can land the helicopter quite safely, which is why from an engine failure point of view alone, if you look at it, helicopters are safer compared to aircraft. But because of the large number of moving parts and flying in very difficult conditions where, let's say in a forest with amidst trees, or in an urban scenario amidst very tall multi-story buildings, there is a possibility of the rotor tips touching, especially the tail rotor, etc., touching something on the way, and therefore those kinds of accidents, of course, are more in helicopters. So always have a pros and cons of different types of flight, whether it's rotary wing or uh, fixed wing. And there's a lot of interest in for drones, especially micro aerial vehicles and nano aerial vehicles, and flapping wings as well. So when they are inspired by birds, we call them as the micro aerial vehicles. When they are inspired by insects, we call them as nano aerial vehicles. In both cases, the aerodynamics is very different, because both cases, compared to passenger aircraft, you have lower Reynolds numbers and therefore larger viscous forces. And those viscous forces are going to cause a lot more drag, and various other complications in terms of the boundary layer, etc., which again has an implication for us as structural engineers in the structural analysis that we do, because those loads have to be accounted for, not in a resultant sense, because many problems that you would have solved in statics, for example, the course that you did on statics, you would have seen that you can take the resultant force or a resultant moment and work out the solution. That doesn't help in this case, because the complex distributions that are there will cause very different stress strain distributions compared to the resultant, especially closer to the points of application of the forces and moments, because the so-called Saint Venant's principle is not valid over there. The Saint Venant's principle says that if you go a distance which is of the order of magnitude of the cross section into the interiors, then it doesn't matter how you're applying a load at this point. I can apply either a concentrated force, or I can apply a distributed pressure, both of which, the resultant of which is the same as the force that I was applying earlier. And only things will change close to the point of application of the force, that is of the order of magnitude of a distance of the cross-sectional dimension. But once you go into the interiors, it just doesn't matter which way you're applying the loads. So since from an aircraft point of view, all points in the aircraft are important for us, including points which are closer to the actual application of the load, namely the skin of the wings, or the skin of the fuselage, or the skin of the horizontal and vertical tails, the stabilizers, you do need to take the distributions into account as well. So all of these come into picture over there. Then there are the control loads, of course, coming from the aileron and the rudder and the elevator, or if it's an entire tail, horizontal tail, which is rotating, that. And all of these are, of course, the flap deployment for uh, takeoff and or landing. All these kinds of spoilers, for that matter, to increase the drag at certain phases of the flight, especially on the ground, in order to ensure that certain on-ground maneuvers can be done. So all of these are going to cause different force and moment distributions, and each of them has to be analyzed because you don't know a priori which is critical amongst them for which particular structural component and which part of that structural component. So you need to consider them overall and then reach that stage. Um, Also, there's something called the VN diagram, the diagram plotting the load factor versus the velocity, and that essentially creates the boundaries in terms of the extremes that the aircraft has been designed for. And that is an important input for structural engineers. So I'll come to that. We'll actually draw that and I'll explain a few parts of that, though you might be, some of you at least might be exposed to it from other courses or your own self-reading as well, because that's a very, very important input. It's not a part of the structural analysis, but is an important input for the structural analysis, without which a lot that we do will be meaningless, because we need to get to the critical loading scenario. The next thing is in terms of some more secondary kind of loads, the turbulence that is there not only from the air, but the turbulence from the exhaust from the engines. So especially jet engines, when you have the velocity at which the exit takes place, because that's what creates the thrust for you, is so large, and the temperatures are so large, and it's not just air. Remember, it is air which has the burnt fuel in it, and therefore the chemistry of it, the thermochemistry of it, and the overall properties of that exhaust are very, very different. And the way the engine, where it is mounted, for example, if it's on the wings, then the tail could be affected by that. And some of the aircraft, like fighters, have a nose engine, and that can affect even the wings. So you have to make sure that the turbulence that is created by the exhaust, how it is handled or accounted for in the wings as well. And that's where you will see either high wings or mid wings or low wings, though there are aerodynamic reasons for that as well. Even from the point of view of where you're placing the engine, you would want to make sure that the impact of the or the influence of the, I didn't want to use the word impact because it has different connotations in structural analysis, as we already discussed. So the influence of the exhaust should be minimal. That's what we try to see. So because there's a huge wake that is created even when there's no exhaust from the wings to the tail. Added to that, if you have the exhaust from the engines, the turbulent way in which it comes, and the tail is subjected to that flow field, that can cause some other additional issues as well. Then the last thing that I want to talk about in terms of the external load type is the highly convoluted and coupled nature of all of these things. Though we try to, in a beginning course, an undergraduate course like this, or the other courses that you take, we tend to take a piecemeal approach and study each one of these individually. They're all highly interconnected. So in fact, aerothermo-servo elasticity is a topic that has been discussed and studied and researched upon for a long period of time, and has much more practical relevance than aeroelasticity alone, or thermoelasticity alone, or servoelasticity alone, or elasticity alone, which is what we will do in this course. Because elasticity is talking about, at the most, incorporating along with the reactions of the material to the external loads that you're applying. It might at the most take inertial loads into account, not more than that. But in reality, you know that where the source of those loads are coming, aerodynamics, and that aerodynamics can be affected by how the structure responds to the loads. So in other words, for example, the lift distribution is going to cause a certain bending, and that bending is going to change the shape of your wing. Okay. You've seen the tip deflections can be fairly large, and the overall shape changes. And therefore, the aerodynamics changes. So it's kind of a loop, and it has to converge somewhere, and that's why aeroelasticity important. But again, you cannot study without the influence of, especially of when the temperature changes are significant. Those regions, the thermo comes into part. So you have aerothermoelasticity. There are only thermoelasticity in regions where internal part of the aircraft where aerodynamics is not involved, but you have thermoelasticity. You have to look at the interaction between the heat exchanges that are involved and the mechanical energy exchanges in the form of strains that are involved. And finally, servo refers to hydraulics, but in a more generic sense, it's all of controls, because these days it's all fly-by-wire or various other aspects where you're essentially using electrical signals, or even some of the more advanced drones like nano aerial vehicles. You can use signals like Bluetooth or Wi-Fi and things like that, which are essentially wireless. So fly-by-wire, moving on to fly-by-wireless. Fairly advanced ways of control techniques are there. But what is meant by servo here is hydraulics, which was the typical conventional way in which older aircraft were controlled. And some of the current designs are also continue to use that, especially very large aircraft. But in a broader sense, we are talking about when you're talking about servo, we are talking about the forces coming from the control systems, elasticity, the forces coming from as a reaction from the material making up the structure, thermo, essentially because of the temperature changes and heat exchanges taking place between the atmosphere and the structure or different parts of the structure, or because of the engine, fuel burn, etc. And aerodynamics, of course, bringing in the prefix of aero. So that would be a much more realistic consideration to take in. And as I already mentioned in a different context earlier, you can't expect to study each of these individually and eventually stitch them together. Because each one of them, and most of them at least, are non-linear, especially the aerodynamics, the elasticity, and the kind of servo that are used today, the control systems that are used today. A lot of non-linear models are there, which are much more accurate and realistic compared to the linear models. And therefore, when you bring them together, the principle of superposition is no longer valid, and therefore you can just stitch them together. So from right up front, you have to bring them all together. But that's too much of an overkill, even from a pedagogic point of view, from a learning point of view at this stage. So just to understand the overall behavior, we try to look at it from a piecemeal approach, which is all that analysis is all about, breaking things up, both from a overall aircraft point of view into smaller parts. And within the analysis itself, essentially you're not analyzing all physics of that small part also. You're trying to look at certain aspects of the part and ignore certain others for later inclusion. And again, we also talked about in terms of dropping off the four out of the four dimensions, the time to deal with statics, the thickness to deal with plates and shells, and the breadth or the width in order to deal with just the length, or more like a beam kind of a model, or one-dimensional model, which could also be a torque tube, or it could be a shear web, or things like that, right? Or a column or a rod. So, are there any questions in these two, material type and external load type, that we discussed?
I have one question. So
Yeah.
next to bird heads, there's an example of external loads. I wonder whether it says LG next to bird heads.
Can you are you close to the microphone? Because there's a lot of noise.
Can you hear me now?
Yeah, yeah.
Okay. Next to bird hits is external load. Is this like output?
I'm not hearing you continuously. You said bird hits. Is it a mechanical load? After that, I lost you.
So next to bird hits, there's two
Yeah.
letters.
Oh, okay, okay. I'm sorry. Landing gear, I think. Yeah. LG. So and etc. So I'm sorry for my very poor handwriting. So it's essentially the landing gear and other things like that. So most of these are impact kind of situations, so essentially causing mechanical loads. So landing gears, glad you pointed out because I think I also skipped that. So when you're landing, there is an impact kind of a thing, depending upon, of course, how experienced the pilot is and how smoothly he or she lands the aircraft. Nonetheless, you will have certain transfer of loads from the ground through the tires to the rest of the landing gear system, and then therefore to the aircraft. The way the landing gear is attached to the aircraft, it could be tricycle or whatever kind of landing gear configuration you have. So those are very important structural loads that we need to deal with, and that is one exceptional place where, as I think very briefly mentioned earlier, is steel continues to be used. And this will be kind of handy for your second assignment as well. You will see that though most places it's composites and many places it is aluminum or titanium alloys, especially for military aircraft, you will see that steel is also continued to be used in some very rare, exceptional places. And one such example is the landing gear, because absolute values are important there more than just these specific values. So we're willing to go with some weight penalty in some of those locations. Anything else?
That's all the questions we had.
Okay. Okay, so I just have 10 minutes, so I'll just complete the other two as well. The next way in which, remember, all of these are classification basis. And can did you say something? Okay. So glad you muted it. So flight phase is what we're going to be talking about next. So depending upon the flight phase, whether it is takeoff or taxiing, even before that, taxiing, takeoff, or just even being stored in a hangar. That is because there's a self weight which is there, even when it's just on the hangar, not even moving around. So there is a certain loading and therefore stresses in the entire structure. Then we come to takeoff, TO. Then you have climb, and this is the simplest kind of configuration. You have cruise, as you do in the all passenger aircraft, for example, and you reach a particular location where you want to do something. In the case of a fighter aircraft or an acrobatic aircraft, you do certain maneuvers. Okay. Even in a passenger aircraft, some not so large load factor maneuvers are still there, because if you need to make certain turns, you need to change the flight path or whatever, you need to make certain maneuvers, but they become much more complex when you go to acrobatic or fighter aircraft. Then once that job is done, or in some cases it could be, let's say, a reconnaissance aircraft. If it's a reconnaissance aircraft, then you're dealing with loitering as well. So at very slow speeds, you just want to go around that place which you want to monitor, and send back the feedback to the home system in terms of what you are observing over there. Right. Also important for cartography, which is making maps, etc. Then once you're done with your job, you cruise back to where you need to come, and then you start descending at some point in time, and then eventually landing, once again taxiing and being stored in the hangar or going to the maintenance, whatever. So each of these will create different kinds of external loads from different sources that we already talked about. And each of these will then have to be handled in a different way at different component level, because some of them might be critical for some component, may not be critical. For example, very easy and obvious thing is the landing is going to be the most critical thing for your landing gear, right? So that's a no-brainer. But the other things become a little complicated. Which part of the wing is facing which largest load or largest stress or most critical condition under which phase of flight? So that becomes may not be necessarily the maneuver. It could be some of this those could be in takeoff or in climb. So it's important for us to consider all the flight phases and to make sure that the most stringent condition is taken into account for each part of the structure. So that's as far as the flight phase is concerned. And get to this. What do I have there? Oops. The geometry, right? So the last thing that we're going to be talking about here is the geometry. So in the geometry, it's the undeformed shape of the structure. Based on that, we make the classification. As I said, this is something which is very commonly ignored. So almost all flying vehicle structures can be classified into the first two types, which is 1D or 2D. We'll very rarely have a three-dimensional structure. In other words, all three dimensions being of the same order of magnitude. Okay, so very, very few structural components will be like that. Most of them will be either rods, beams, columns, frames, torque tubes, and pipes on the one hand, which are all 1D, or it will be plates, shells, solid, or again, no, that's different. So either plates or shells. So within rods and beams, you can have two types, which is solid or hollow cross section. And within the hollow cross section, as I already drew on the blackboard in the class on the first day, it could be either thin walled or thick walled. I drew only thin walled over there because that's the more common one. But there could be certain places where you might need thick walled, especially if the internal pressure is large and therefore the hoop stresses are large. You may or may not have heard these terms, but if you're not, I'll cover that in a later class. So when there's a pressure vessel which is cylindrical in nature, you have stresses along the circumferences, which is hoop stress, and along the length of the cylinder, which is longitudinal. And those things you need to be aware of. And depending upon the pressure levels, sometimes we need a thick walled cylinder. But most constructions in flight vehicle structures will be thin walled. And within thin walled, as I already discussed, you could have either closed section or an open section that you see over here. And then coming to the beam, we call it the beam, but most literature, as I said, when they say beam, they refer to only bending, but we deal with axial loads and torque as well. So when we deal with axial load, depending upon whether it is tension or compression, you might call it as the rod or the column respectively. So if it's tension, you call it a rod. If it is compression, you call it a column, right? Then we go on to combination of beams. So you could have a fairly complex shape of a beam, like just like a door frame. Okay, so around your door, you have a frame. So that can take on complicated shapes. We will see there are certain frames like that on an aircraft. Some of you might be already familiar with the bulkheads, for example. So when you have bulkheads in between, it's not at the ends of the aircraft, it takes the form of a frame, and we'll see the reasons for that in a much more detailed manner, most probably in the next class. Then we talked about torque tubes, especially when you're trying to deliver along the shaft. For example, in the helicopter from the main rotor to the tail rotor, there is a drive shaft which is running from the engine in order to drive the tail rotor as well at the desired speeds, which can of course be controlled by the rudder pedal of the helicopter pilot. So that's just an example, but there could be many other locations where there are torque tubes. So these are typically thin walled tubes, usually circular, but could be elliptical and or rectangular or square as well, a good cross section, usually thin walled. And then they are subjected to torque at both the ends, or torque at one end, the other end is fixed or whatever. So based on that, and even if you're looking at just the wing itself or the aircraft wing, because of the pitching moment that is there, uh, you remember that the entire pressure distribution and the shear distribution on the wing can be reduced to a lift force distribution along the span, a drag distribution along the chord, and a pitching moment, which is having an axis which is parallel to the span. So this particular pitching moment is actually like a torque for the box beam that is there within the wing, the skeletal structure. Okay, so all of these are based on the geometry. You have the various classification. Some places you have pipes, which is essentially your fuel pipes transferring the fuel from the fuel tanks wherever it is stored to the engine at the given rates, which is of course controlled by the throttle of the pilot. Uh, then you have again, in terms of the cross section itself, it could be either symmetric, asymmetric, which is not symmetric, and it could be axisymmetric, as in the case of a circular cross section. So some of these things like symmetry and or axisymmetry will bring simplifications to our model, and therefore the analysis becomes simpler, and some of the challenges can be overcome, and many of these might even be amenable to analytical closed form solutions, which give a lot of insight into the physics of the problem. Okay, so I think with that, I come to the completion of today's class. If there are any final questions, I'd like to answer them. Okay, then I'll see you in person tomorrow at CVH. Bon appetit. Goodbye.
Thanks.
Bye-bye. Take care.